Okay, well, I'm going to stop my share now, and we're going to get the show on the road. Hi, everyone. Thanks for joining us today. I'm Kate Thornhill. I am a digital scholarship librarian at the University of Oregon, and I am going to be moderating our presentations today. And I'm joined here with my colleagues, Tara Perillo at the University of Oregon. Tara will be managing all of our Zoom logistics. So if there are any technical issues, Tara is here to assist. We're also excited to be here with Samuel Karlson, Piper Gray from the U.S. Air Force Academy, as well as Blake Hardin and Megan Walter from the University of Oregon. We are going to have 4 lovely and awesome presentations, and I'm going to ask our presenters before they share their slides to please introduce yourself with your name, your affiliation, and your major. With that, I also want to say presentations are between 10 and 12 minutes long with about 5 minutes of questions for individuals. And then we will be moving on to the next presentations, but finally we'll be wrapping up with 15 minutes for panelist questions. If you do have any questions, you're welcome to raise your hands and ask on the mic. And if the chat feature is available, you can also ask those there in the Q&A or in the chat. We'll be monitoring. So we're going to be going in order of our schedule. So first, we're going to have Sam. Sam, you are welcome to share your screen and introduce yourself. And I'll be keeping time for you. And Sam, just so you know, you are muted.
All right, perfect. Can you see me now? Or hear me now, sorry. All right, I'm gonna reshare, give me 1 second. All right, can everyone see and hear my presentation?
You are good to go.
Perfect. Well, thank you so much. I want to give a big shout out to the U of O for letting us present here. Me and Piper, like we've mentioned, are from the United States Air Force Academy, and we've been allowed to present here, and we're so grateful for that opportunity. My name is Sam Karlson, and this year I've been doing research in radiation trapping in potassium. And I actually had a partner in my research. His name is Ryan Dindorf. And I had several mentors from the United States Air Force Academy. So a special thanks to Dr. Monte Anderson, Dr. Brian Patterson, Captain Anita Dunsmore, and Lieutenant Colonel Robert Vinson for helping me out with my research. So to give a brief overview, basically I'm going to go through the methods and procedures for our research, the results that we found, and the future directions that I hope to go in the future with this research. To give a little bit of an overview, I'm a physics major, and what basically we're studying about radiation trapping, which is essentially that photons are trapped in a system by continually being absorbed or re-emitted by atoms. So to give an example of this, what happens in the center of the sun, a photon will be created in the center of the sun, and it'll be continually reabsorbed and re-emitted by atoms in the sun. And so it can actually take up to 100,000 years for a photon that's produced in the center of a sun to actually escape outside of the sun. And so that is what radiation trapping is. And for our research, we wanted to use a Monte Carlo simulation to basically study the effects of radiation trapping in potassium atoms. And I'll explain a little bit why in just a minute, but the idea was to build a simulation and then compare that with experimental data to measure the excited state lifetime measurements for potassium. So just to give you a quick understanding, the application for this is for gas lasers. Radiation trapping is a source of systematic error in excited state lifetime measurements. And so basically, as you build models for gas lasers, it's really important to understand all the different effects, including radiation trapping, which has been a really big problem for what are called DPALs, diode pump alkali lasers. And the Pentagon is actually has a high energy laser scaling initiative, which it hopes to basically scale lasers up and have more powerful lasers. And one potential option is the DPAL laser, like I mentioned. But in order to do that, we have to understand radiation trapping a little bit better in order to create those lasers. So on the experimental side, my friend Ryan did a lot of the research in the actual experiment. And this is just a little bit of a setup of what it looks like. Basically, to summarize, we had to, shoot the laser through what are called EOMs, electro-optic modulators, so that basically one pulse from the laser would actually enter the vapor cell. And then you can see in the bottom right, the thing labeled K cell is where the actual potassium vapors are. And the laser will enter the cell, be absorbed. The photons would be absorbed and re-emitted by the potassium atoms, and then be detected by the PMT, or the photomultiplier tube. And in order to understand how to simulate this, we basically had to understand the probability that an atom would absorb a photon. And that required an understanding of the hyperfine structure energy levels for potassium. So if you can see on the left, basically we excited the atom from the S1/2 orbital to the P3/2 orbital. And we had to take into account the hyperfine structure energy levels, the F and J quantum numbers. And so for the S and P orbitals, there were several F quantum numbers that we had to take into account. As you can see on the right, this is what's called the line strength factor, or the relative probability that a photon would excite a potassium atom from each jump. So from the F equals 1 hyperfine structure energy level to the F equals 0 hyperfine structure level from S to P3/2, it has this relative probability. So without temperature or pressure changes, the actual line shape for a potassium atom would have a Lorentzian distribution of just a few megahertz. But because of pressure and Doppler broadening, the actual distribution is what's called a Voigt profile, or a convolution of a Lorentzian and a Gaussian profile of several gigahertz, as you can see here. And so basically, this enabled us to calculate the absorption cross-section, or the probability that a photon would be absorbed by a potassium atom. And as you can see, we were actually able to simulate what the distribution would look like. So the absorption and find what's called the absorption coefficient, or essentially how far the photon is likely to travel before being absorbed by a potassium atom. So in order to create the Monte Carlo simulation, or the computer simulation, we basically had to follow these steps. We had to calculate the absorption coefficient, or like I said, the probability that how far the photon is likely to travel before it's absorbed by the potassium atom, and then generate the following variables: a random photon frequency near that D2 absorption line, or basically the jump between the S1/2 and the P3/2 orbital, a random location inside the cell for the absorption event to occur, a random decay time consistent with the natural lifetime, and then a random direction of frequency for that emitted photon to travel. And then you basically repeat that process until the photon escapes, and then they record the total accumulated time. And that helps us calculate the excited state lifetime for potassium. So this is just a quick visual of what it looks like. So essentially, the incident laser goes in through the window, is absorbed and then re-emitted by potassium atoms, and then will escape through the detection window. And where it is, we count that. So this is an actual example of one of our simulated results. So on the left, you can see in our simulation, these were photons and where they were absorbed, so the initial absorption sites. And on the right are the total absorption sites. So as you can tell, because of the greater number on the total absorption sites, you can see the secondary and tertiary absorptions, basically demonstrating the radiation trapping. Here's another, basically the same visual, only from a top-down view or side view of the vapor cell. So these were our simulation results. As you can tell, it actually follows the appropriate exponential fit that we expect to see from the experimental data. And by using linear regression, we were able to calculate the simulated lifetime for potassium. And then using the experiment, so we were able to compare those simulated results to the experimental results. And this was essentially basically on the left, you see the big line shooting up is the initial incident laser pulse. And if you look way down here, right next to it there, you can see the exponential data. So we had to truncate that data a little bit in order to find the actual experimental fit, which using regression, we could use to find the decay lifetime. For this example, I think this was about 100 Kelvin. You can see that the decay lifetime is approximately 180 nanoseconds. And here's just another example of our linear model and fit. For this example, at 600, we use different buffer gas pressures. For this one, it was at 100 degrees Celsius and 600 torr, which means essentially that we had helium gas in the vapor cell, which changes basically that distribution of absorption coefficients that I mentioned earlier. And so when we calculated the results at different temperatures and pressures, we basically saw that the decay lifetime increases as the temperature increases and decreases as the pressure increases. And this is essentially the same, just at additional temperatures and pressures. So we compared our computer simulation to our experimental results. And if you look at the table, you can actually see that there's quite a big difference between our experimental lifetimes and our simulated lifetimes, which basically demonstrates that we need to continue working on our computer simulation. But the good news is, as you can see, as temperature increases for both the experimental and the simulation lifetime, as the pressure increases, the experimental lifetimes and simulation lifetimes decrease. And as the temperature increases, the lifetimes for both the experimental results and the simulation results increases. So even though our numbers aren't quite right, we can tell that the trends are appropriate and that we are pretty close to achieving the right results for what radiation trapping would look like in a simulation. So just to give a final conclusion, we're not quite there yet. We need to keep working on our simulation to basically make it so that it actually matches the experimental results that we found in our lab. So we're going to fine tune that simulation, but we're going to keep compiling additional data points at different temperatures and pressures to ensure that our model is accurate. And once we do that, as I mentioned, the application is to understand the effects of radiation trapping to help build gas lasers. So these are some of the references we used. Are there any questions?
Great, thanks, Sam. If folks have questions, please feel free to use the chat or raise your hand. So Sam, I have one question for you. So I am not a physicist or a scientist. And I was curious if you could tell me with the gas lasers that could be used, how does your research how could that be used by other scientists that apply it?
Yeah, absolutely. And so here, I'll go back to this slide in our application slide. Basically, one of the problems is, so I didn't really go over this, but the main issue in these gas-powered lasers is that it's really hard to keep the beam quality when the power goes up. So the more power you use, it's harder to keep the beam quality. And essentially, one of the problems is it's hard to experiment with it. It costs a lot of money. It takes a lot of energy and whatnot. And so the idea is if you can simulate it on a computer, then you can run a lot of tests without actually having to build or use the experiment. And so by doing that, essentially, if you can study all the different effects that could be problems, you can mitigate that without having to run the experiment and figure it out by testing it. So basically, it's a way for us to help simulate building these bigger lasers.
Cool, thank you. So we are at time. So Sam, thank you so much for a great presentation. And just to remind folks, the last 15 minutes of this session will be open for questions for everybody. Okay, so next we have Megan. And Megan, you're welcome to share your screen, unmute yourself, and I'm going to pass the mic to you. If you could introduce yourself, your major, what university you're with, and can't wait to see you do your thing.
Yes, hello. My name is Megan Walter. I am a math and computer science major at the University of Oregon. And my project is titled On the Multifractal Structure of Observed Internet Addresses. So I'm doing networks research. So as the internet grows and as more devices connect to it, the number of internet attacks and network mismanaged significantly increase. Determining the traffic responsible for causing these issues is difficult though. So observations about benign traffic characteristics are critical when trying to develop monitoring techniques. So we are basing our work off prior studies that have shown that internet traffic exhibits various fractal and multifractal behaviors. Before we go, I want to go over a few terms that I'll be using throughout. So a connection or a flow is a collection of data packets that are flowing between two computers across the internet. An IP address is an identifier that determines the source and destination computers of the data packet. We will be specifically looking at IPv4 version 4, which is a representation or format of IP address made up of 32 binary bits. And an address prefix will refer to the first P bits of an address. So if two addresses share a prefix of length P, that means that they have the same first P bits of the address. And the reason why we're sort of looking at IP addresses as a way to determine the structure of these flows is because internet traffic with shared prefixes have some correlations with one another. The way that they're assigned is that blocks of IP addresses are sort of assigned to different organizations and then dispersed throughout. So for example, if a network has been infected by malware, the adjacent prefixes underneath that block will likely also be affected by that. So going back to sort of what fractal and multifractal properties means. Well, a fractal is an infinite pattern that repeats itself at different scales and can be described by a fractal dimension, which indicates the complexity of the fractal at different scales. And a multifractal is a generalization of this fractal, a monofractal, where a single fractal dimension cannot sufficiently describe its scaling properties. Instead, the system can be described by a spectrum of fractal dimensions. In the context of IP addresses, we can think of each prefix length as a spatial scale. So prior work in this subject provided evidence for multifractal behavior in the address space and demonstrated provided multifractal models to represent the address structures over short-term periods by approximating the multifractal spectra of their data. And some proposed applications for these models were reducing unwanted traffic or simulating real-world traffic data to be more realistic. However, there are a few issues with this prior work as these studies were conducted over 10 years ago, and then the data sets used are considered small and outdated by current standards. And there are a few issues with the analysis methods that they used, which was the multifractal spectra method, as it's limited in the context of this particular type of data. And I'll go more into that a little bit later. So building off of this prior work leads to these key research questions that we were looking into. The first being, is the structure of IP addresses observed on a modern campus network still consistent with the multifractal hypothesis set out in prior studies? Two, how does the duration over which IP addresses are collected, so like the time window that we look at, that we observe and take IP addresses from, impact the multifractal structure of observed addresses? And how does the multifractal structure of observed addresses evolve over time? To answer this question, we used a data set that it was made up of net flow data connected by University of Oregon border routers over the course of 9 years. So net flow is simply a measurement utility in a network router that captures information for each connection. Some examples can be seen in this figure. So the net flow data is stored in sort of 5-minute bins that we can then go into and extract. But there are a few challenges with the organization of this data in that flows may not necessarily be organized into the correct time bin. So if a file is named, okay, this is at midnight on this day, well then it will cover like 5 minutes from midnight, but something within that time frame may also be found in a later time bin. These flows may also be split into fragments, and there was also just a lot of data, several million flows for each 5-minute period, which introduces difficulty in processing it. But given this data, our goal was sort of to convert flows active during a time period into sets of distinct external IPv4 addresses. So if we were given, say, 30 seconds, for example, and a start time, then we would consider all of the flows active during this time period that were observed by the router and create a set of the distinct active external IPv4 addresses that were observed during that time period. So to answer the question, sort of how does this change over time, we took a look at 3 different timescales and also changed the duration of collection for each of these timescales. So we have a 24-hour timescale in which we had a collection duration of 30 seconds, a 60-day timescale where we had a duration of collection of 30 minutes, and an 8-year timescale that had a collection duration of 24 hours. So if we look at sort of the distribution of the number of distinct addresses over these timescales, we can see that the 24-hour timescale had approximately, between 12,500 and 22,000 distinct addresses per epoch. The 60-day sample is then increased by a large magnitude. We have between 100,000 and 250,000 addresses per epoch, which makes sense because we've increased the collection duration to 30 minutes. And the 8-year time scale has a large range of number of distinct addresses from 100 million and about 10 million. So to go into sort of the methodology, we wanted to essentially circumvent the issues that were created in prior work by using the multifractal spectra analysis. So there's 2 descriptions of multifractal structure, geometric and statistical. We've already sort of discussed the geometric structure. Multifractal formalism is a theorem that relates the geometric description to the statistical description. So given certain circumstances, the results of these 2 methods are equivalent in demonstrating the presence of multifractal behavior. Excuse me. The multifractal spectrum method used in prior work generates a geometric description. However, it doesn't really work in the context of IP addresses because it assumes an infinite amount of spatial scales on a data set where we're considering 32 spatial scales with the prefix lengths of the IPv4 addresses. Our method of moments method generates a statistical description, which is more accurate to a data set with discrete number of spatial scales, and is also just in general easier to compute. To perform this analysis, we first got multi-resolution quantities represented by the expression mu. And essentially what this does is it counts the number of observed addresses that start with each prefix. So each prefix is associated with a certain number of addresses. And this gives a sense of the distribution of IP addresses across the address space. We then used those multi-resolution quantities and calculated the sample moments for a range of moments. In this case, it was -4 through 4. And generated a structure function, which essentially is represents some characteristics of the IP addresses across the address space, depending on the prefix length. We then used a partition function, which estimated the slope of each of these traces so that we got a sense of the scaling behavior across all of the moments. And multifractal formalism gives us the idea that it suffices to show that the partition function is nonlinear. That is sufficient to show that the data is showing multifractal behavior. So to show this, we use the R-square value generated using linear regression to estimate the slope of this partition function, where closer to 1 implies more linear and closer to 0 implies less linear. And here's an example of such a plot over all of the samples in the epoch. So this is over time, and this is the R value over those times. So as for the results, you can see here for the full range of prefix lengths, 1 through 32, we can see that the structure function can be separated into regions of distinct behavior. So here it is different than here, is different than here. And thus the partition function is unable to reflect the differences between these regions. So we decided to limit our scope to a smaller range of prefix lengths from 2 to 12. And so here is some results from that. This is from the 24-hour timescale, and this is from the 8-year timescale. So this is the 30-second epoch, and this is the 24-hour epoch. And as you can see, the partition function has a very, very similar shape to it, although the scaling is slightly different. So this sort of demonstrates the consistency of the multifractal behavior across different durations of collection. And so the R-squared plots given by these partition functions over time show that the like fairly high R-squared values. That's sort of to be expected considering how the R-squared value works. Normally it would be like scatter plots, but this is like a fairly linear trace. However, there is a shallow dip around 9 a.m. Up until 6 p.m. for the 24-hour time scale. And we can see a shallow trend of decline in the case of the full year. And this sort of represents we can sort of see that as the network gets busier, so over time it's gotten busier, during the day it's gotten busier, we can see a correlation between this busyness and the demonstration of more multifractal behavior. So basically, in conclusion, the results of this work demonstrate evidence that the real-world IP addresses exhibit multifractal behavior across all of the timescales, and they also indicate a correlation between the network being busier and stronger multifractal behavior. This is encouraging as busier networks are environments in which network management solutions are more critical. And essentially, we have provided a new technique of multifractal analysis for IPv4 addresses. A few aspects still need to be worked out. However, this method can provide a more robust set of evidence for the same claims. And hopefully this contributes a meaningful basis to rethink current internet algorithms to become more spatially aware. And a big thank you to Dr. Reza Raje and Chris Misa for their guidance throughout this research project. Thank you very much.
Thank you so much, Megan. And so you can stop your screen share and we're going to open it up for questions. Does anyone have a question for Megan? Please use the chat. You can raise your hand if you have it. Well, I have a question for you.
Yes.
What did you find to be the most challenging part of conducting this research?
I think that a challenge that I had in this was, learning about the way that different mathematical concepts differ depending on the context that you're in. So a multifractal will look extremely different in the case of IP addresses versus, say, an infinite set of numbers that is generated using like a mathematical rule, because there is like a difference between the infinite and the discrete, and sort of shaping shaping one's process in order to fit the data, to fit real world data is, I think probably the most challenging part of this process.
Great, thank you. Any other questions before we move on to our next presenter? Okay, so thanks, Megan. Awesome. So next we have Piper. Piper, please introduce yourself, your university, as well as your major. And the floor is yours for sharing your screen. Oh, I don't know if we can hear you. Are you able to hear me? That's okay. Don't worry about it. It's no problem. How about this, Piper? How about we have Blake go and then you can come back in? What do you want to, would that be helpful? Okay, cool. Awesome.
Okay, so should I go or are we gonna wait for her?
Yeah, we'll you go and then we'll have Piper go. We'll have Piper go.
Okay,
last.
cool. So just a disclaimer, my topic doesn't actually have anything to do with inner space or the internet. I just tested positive for COVID on Monday, so I wasn't able to present in my group in person, so I got moved to this group. So just to clear up any confusion before I start, but I'm Blake Hardin. I'm from the University of Oregon, and I'm a global studies and economics major. So let me, okay. Okay, so it should be sharing, right? Let me know if you have any issues seeing that.
You are good to go.
Okay, awesome. So I did my project on COVID-19 vaccine intentions for people who inject drugs here in Lane County. So I want to start by thanking my primary advisor, Dr. Melissa Grayboys, and my secondary advisor, Dr. Camille Chaffee, as well as the 4 organizations I have listed here. So HIV Alliance, Prevention Science Institute, the National Institute on Drug Abuse, and the UO Undergraduate Research Opportunity Program. So to start off with, just to give a brief roadmap on where I'll be headed in this presentation. So I'll start off with just the background and sort of my personal motivations driving me to this project. Then I'll look into the specific research questions that I asked and the methods that I used to find answers to those research questions. And then I'll give you some brief highlights on the main findings from those questions, and then how that led me to proposing a new framework for conceptualizing vaccine hesitancy among people who inject drugs, and sort of the conclusions of that framework and of my findings. So as I mentioned, I'll start with some background, and there's really two main points that I want you to keep in mind throughout the presentation. So first is that in the past research, people who inject drugs have exhibited greater levels of vaccine hesitancy, and that's true for common readily available vaccines like hepatitis A and B vaccines or annual influenza vaccines, but it's also true for hypothetical vaccines that are highly related to people who inject drugs. So things like HIV/AIDS or hepatitis C. And then the second thing is that people who inject drugs face higher mortality rates from infectious diseases. And many of those infectious diseases are the same as the ones that they exhibit higher vaccine hesitancy towards as well. So things like influenza, hepatitis A and B, HIV/AIDS, and upper respiratory illnesses. So to dive in on that vaccine hesitancy point a little bit more, for this project, I defined vaccine hesitancy as the level of uncertainty an individual exhibits when they're provided with the opportunity to get vaccinated. So essentially what that means is that vaccine hesitancy lies on a gradient, and everyone has some degree of vaccine hesitancy for every vaccine preventable disease there is. And this definition mostly coincides with the working definition offered by the WHO and fits within the predominant model that's used in most vaccine hesitancy research to date, which is the WHO's 3Cs model. And that model speaks to three different categories that affect vaccine hesitancy according to the WHO, which are confidence, or the level of trust or distrust a person has in vaccines, vaccine providers, or the government; convenience, which speaks to the ease with which an individual can access vaccine services; and complacency, which speaks to how motivated an individual is to receive a vaccine when it's available. And then as another note, as I mentioned prior, people who inject drugs have exhibited higher levels of vaccine hesitancy for several relevant diseases compared to the general public, but there's very little research that uses qualitative methods to look into what the motivators for that vaccine hesitancy are. And that's sort of the space that my project occupies. And then on the second note, so people who inject drugs face higher risk from COVID-19, both in contracting COVID-19 and passing from COVID-19. And those risks sort of boil down into two primary categories. So there's physiological risk factors, which are things like higher frequencies of upper respiratory illnesses or autoimmune diseases, which exacerbate COVID-19 symptoms and result in greater susceptibility or higher rates of mortality from the virus. And then there's social risk factors that are a direct result of the stigmatization surrounding drug use. So people who inject drugs often face poor social determinants of health, which are things like unstable housing or low socioeconomic status. And they also have limited access to consistent healthcare services. And additionally, even when they have access to traditional healthcare, they've reported frequent discrimination and dehumanization, which disincentivizes them from accessing those services, even if they're technically available. And so all of these things sort of work in tandem to heighten the risk from COVID-19 for people who inject drugs. So now moving into the research questions that I asked. First, I wanted to see whether these patterns were also exhibited for Lane County's people who inject drugs related to COVID-19. And second, I wanted to see what the key motivators that were driving people who inject drugs to accept, delay, or refuse the COVID-19 vaccine were. So I wanted to see both sides of the argument, so see why people were choosing to get vaccinated, but also why people were choosing not to. So then for the methods, my study relied on a convergent mixed methods design. So this meant that I drew on both quantitative and qualitative data to come to my conclusions. And under this specific convergent design, data are collected simultaneously, so in the same time period, which for me was July through September of 2021. But they're analyzed separately initially. So you do qualitative analysis and you do quantitative analysis, and then you sort of see where those two types of analyses agree and disagree. So for both of the qualitative and the quantitative components of this study, all data was collected at several HIV Alliance syringe exchange locations here in Lane County, where U of O is. And so essentially syringe exchanges are places where people who inject drugs can exchange used syringes for new ones and get other necessary supplies that allow them to maintain their health. And this was especially important during COVID-19 because it also became a place where clients could get COVID-19 information, testing, and vaccines. For my qualitative data, I relied on 41 semi-structured interviews where my goals were to learn why HIV Alliance clients were choosing to get vaccinated or not, and also to give them a platform to share their experiences and their stories from living through the COVID-19 pandemic. And to do that, I recorded all 41 interviews and transcribed them and then coded them, which is essentially, I identified themes as I read through the transcribed interviews and then refined those themes and read through the interviews again after having come up with these specific themes and sort of saw where they applied in each interview that I did. And then in my presentation of the data, I relied heavily on quotes from people I interviewed, which for these slides will be present on orange boxes. And then for the quantitative data, I used 260 surveys that were actually from a larger study examining a COVID-19 testing initiative at syringe exchanges in Oregon. But for my project, I used these surveys to first provide a gauge for vaccine rates among HIV Alliance clients, and also to establish what, if any, demographic characteristics were correlated to high levels of vaccine hesitancy. And to do this, analysis was done in R and involved both descriptive statistics and linear regressions. So then for my results, first, the quantitative data showed a 33 percentage point difference in vaccination rates for the total Lane County population when compared to the 260 clients who participated in the quantitative survey. So obviously, this is a big gap, and not all of it is due to higher vaccine hesitancy. There's also questions of differences in accessibility to consider, but the surveys were conducted in a period when the vaccine was readily available, including at HIV Alliance syringe exchanges where I did these interviews, and was free of charge. So it does suggest that there's vaccine hesitancy that explains some of the disparity in this vaccination rate. So then for this next section, I focus on the effects of the COVID-19 pandemic for clients at HIV Alliance as they presented to me. So first, this table that I have here, the highlighted sections on the table show clear and strong negative correlations between educational attainment and unstable housing status. So in other words, lower educational attainment and unstable housing both reduce desire to get a COVID-19 vaccine. And so this suggests that social determinants of health might affect vaccine hesitancy. Furthermore, the same social determinants of health that might affect vaccine hesitancy were also worsened by the pandemic. So as the two clients, quotes from the clients that I've included here exemplify, COVID-19 left clients with reduced access to resources that they previously relied on, and also with reduced income. But the interviews also displayed the positive role that community health organizations like HIV Alliance or other similar organizations can play. So HIV Alliance's ability to maintain consistent services during the pandemic was a huge boost for its clients. It was especially important once HIV Alliance started offering COVID-19 information, testing, and vaccines, because this became a space where clients could come to receive supplies that they had normally relied on, but also sort of supplement that with additional COVID-19 supplies. And then furthermore, the reliability that HIV Alliance maintained also built greater trust between the organization and its clients. So this allowed HIV Alliance to leverage this existing trust among their clients to encourage them to take advantage of available resources and also to learn more about COVID-19 to come to a more educated vaccine decision. So then with all of these findings in mind, I kind of felt that the WHO's model wasn't capturing the influences of the social and environmental context of vaccine decisions. So instead, I proposed a 5Cs model that draws on some of the strengths of the WHO's model, but also considers the broader set of issues explaining vaccine hesitancy. So my model reports 5 different categories that describe vaccine hesitancy motivators. I kept confidence and convenience the same as the 3Cs model. So again, confidence refers to trust or distrust in vaccines, and convenience refers to how easily someone can get vaccinated. But then I proposed changing complacency to concern, because I felt that complacency came with negative connotations. And I also added 2 factors, communication and convenience, which speak to how easily or how a person's environment can affect their vaccine decision. And then finally, as you can see, each of these factors is directly influenced by social determinants of health. So it's sort of this overarching thing that's affecting vaccine decisions, which are then stratified by 5 different categories and ultimately combined to determine a person's level of vaccine hesitancy. So then just to conclude, my data suggests that vaccination rates are low, and some of this stems from vaccine hesitancy. It also shows that social determinants of health, like unstable housing and low rates of education, are directly related to vaccine hesitancy. So this means that any strategies to reduce vaccine hesitancy need to address these issues as well. It also shows that social and environmental contexts need to be considered. And finally, that trusted organizations among people who inject drugs are key to addressing vaccine hesitancy and reducing misinformation. And that's it. Thank you.
Thank you, Blake. Great presentation. Does anyone have a question for Blake?
I have one actually.
Sure.
I wonder if you learned anything unexpected, either related specifically to your question or unrelated to your question, and when talking to these folks.
Yeah, so I think probably the most surprising finding for me was out of my 41 interviews, about a quarter of them included some sort of reference to feeling like the government was trying to commit like mass genocide towards people who inject drugs, or a lot of them were also unhoused, so unhoused people. And so obviously that's like a huge proportion of the interviews that sort of centered around this topic. And so I sort of expected some level of government distrust, but I kind of underestimated how big of a role that played.
Thank you.
Mm-hmm.
If folks have questions for Blake, you're welcome to put it in the chat, raise your hand. Okay. Thanks, Blake.
Thank you.
We are now going to have Piper present.
Hopefully, if everyone can hear me. Excellent. I shall get to present today.
Awesome.
I apologize for the technological difficulties. Sam and I just graduated from the academy, and when you graduate, they re-image your computer. So this is my first day with a completely brand new computer, and I don't know how anything works.
No problem at all. Well, the mic is yours, and please introduce yourself, your affiliation, and your major.
So my name is Piper Gray. I am a recent graduate of the Air Force Academy. I was a physics major there, and I worked this last semester on my project. Can everyone see my screen?
Yes, you are good.
Perfect. So the project that I worked on is called the spectroscopy of radioactive xenon using atom trap and trace analysis. I had a partner on this project who's not here with me today. His name's Second Lieutenant Jonathan Sofer. Really quick shout out to all the project mentors. I worked with Dr. Michael Schaefer and Dr. Monte Anderson, all of the US Air Force Academy. And then we also received support from the Defense Threat Reduction Agency, the Nuclear Science Engineering Research Cup, and the Air Force Technical Application Center. Really quick overview before we jump in. First, we're going to do the introduction, talk a little bit about laser cooling and trapping, xenon atomic physics, methods and procedures, data acquisition, current progress, and then conclude. First, the motivation to measure radioactive xenon isotopes comes from the need to identify when nuclear weapons have been detonated or tested in order to make sure that people are maintaining their nuclear treaties. So what we do is we fly in with a sniffer plane, and then we collect the air sample. And then from the air sample, we can determine what isotopes of xenon are present in the air. There are certain isotopes of xenon that will only be present in the air if they've just recently emerged from a nuclear detonation or a nuclear test. And therefore, we can back out exactly what kind of nuclear weapon was detonated or tested, when it occurred, and where. The current method of doing this is called the Swedish Automatic Unit for Noble Gas Acquisition. And there are a couple of minor drawbacks that we're hoping to assist in remedying with this method that we're proposing. So SANA divides the products into beta gamma coincidence counting. So basically, as a xenon atom decays, the radioactive xenon atom decays, it'll release not only a beta particle, but also a gamma particle at the exact same time, which is a very unique signature. So it divides the beta gamma spectrum into several regions based on that coincidence counting. And then as that builds up, then we can identify the profile that we have that will show us exactly what kind of xenon we have. The issues are that there's overlapping counts between isotopes and isomers of interest that limit the functionality of this process. Also, you have to wait for your sample to decay before you can get any information out of it. And it's not the best position to be in, where by the time you get information from your sample, it is already gone. And then finally, one of the other problems is that not all radioisotopes of xenon are beta gamma decayers. So not all of them exhibit this very unique signature. So we're hoping to remedy that. So the principle of laser cooling and trapping is that photons can impart their momentum onto the xenon atoms as they travel down our cooling tube, and the laser cooling spatially confines the atom. And then as we continue to impart the momentum of the laser onto the xenon atom, they're also be momentarily excited and then fluoresce as they relax. And so we'll get them into a cycling transition in which they're repeatedly exciting and then relaxing. So you get a very definitive glow in the center of the magneto-optical trap, which I'll talk about a little bit later. This shows the most important characteristic of this process, which is that when you're using laser cooling, there's a very specific frequency that will work for a very specific isotope or isomer of xenon. And so unlike the SANA process, we get this really nice delineation where there's a very specific frequency that's distinct from all the other frequencies that will only trap one particular isotope or isomer of xenon. And so you don't have to wait for that statistically significant data to build up. Instead, you automatically know exactly what it is if you get a fluorescence at a specific frequency. So each energy level has unique energy difference and unique trapping transition frequencies. This is known as hyperfine splitting, where even though you have xenon atoms that are very, very similar, and the only difference is that they just have a couple, like a slightly different number. So you have xenon 132, xenon 134, they're going to be slightly different. And so a slightly different laser frequency is going to work the best at exciting those atoms into the cycling transition, so we get that nice fluorescence. So we use laser scanning to search our signals for these types of xenon. And so we use a modulated signal. And the reason that we do that is because sometimes there can be confusion with the laser trapping system between the carrier and the reference. If you're moving the carrier frequency, then it will tend to jump and do some things that we're not necessarily are not necessarily helpful to collecting data. So instead we move these smaller bars and we keep the carrier frequency in one place. So this is the setup that we have in our laboratory. On the left side here, where it says xenon gas in, that's where we send the xenon gas into the chamber. And then that large bowl shape is where we prepare the xenon discharge to go into the xenon slower. And then we have a series of 2 collimation chambers. So collimation takes our xenon gas that is, a Boltzmann distribution. So it has all kinds of different velocities and temperatures of the atoms are going in all these different directions. And we take that and we turn that into a very definitive beam of xenon atoms, which are all traveling in the same direction at the same speed, but they're traveling very, very quickly. And so we have to send them into the xenon slower, which is a pre-cooler, which will take them from an order of magnitude of about 10 to the 3rd meters per second to something like on the order of 10 meters per second. And so it slows them down significantly so that we can trap them much more easily. The xenon slower works by, we have a laser that comes down, it's anti-parallel to the direction of the xenon atoms traveling. And so because of our collimation, all the xenon atoms are traveling in the exact same direction and they're traveling directly anti-parallel to our pre-cooling laser that comes in from the right side. And then when they move into the magneto-optical trap, then we have a series of 6 mutually perpendicular lasers, as well as magnetic field, that assist in trapping the xenon atoms into one definitive volume within the magneto-optical trap that we image with the camera. And using the camera, we can detect when we have the fluorescence, and then we can back out at what frequency of the laser as we're scanning it that fluorescence occurred. And then that will tell us exactly what isotopes of xenon we have within our sample. And once we know what isotopes of xenon we have, we can tell whether or not a nuclear detonation or test has occurred, exactly what kind it was, how long it's been since it occurred. There are 2 different ways to operate this, the closed or open loop operation. The only difference is that with the open loop operation, the xenon gas that's not automatically trapped will go back through. And what that does is it helps us trap very, very small amounts. So even if there's only 1 or 2 atoms of a very rare xenon isotope, we can detect it in an air sample. The data acquisition collects 3 different pieces of information for every data point: the integral value of the image, the wave meter frequency, and the current scanning frequency. The integral image data provides a measure of the image brightness that tells us whether or not we have a trapped ball of atoms in the magneto-optical trap. The wave meter frequency should remain unchanged through the entire data taking process. And so that's our check to see whether or not something has gone wrong. If we're getting weird data and the wave meter is changing, then that means that something is going wrong with our laser or something is going wrong with the other systems. And so that's how we make sure that nothing is going wrong when we're testing the actual data. And then the scanning frequency is measured relative to the reference frequency, which is the wave meter frequency. And we log that so that, as I said, we can go back and we can see at which frequency we had fluorescence. And then from there, we can tell what xenon atom was fluorescing, what xenon atom we had trapped. This picture here is a picture of xenon atoms that we trapped in the MOT back in January. So you can see that it's a very definitive glow. So the project goals this semester, this project has been going on at the Air Force Academy for quite a while. The project goals this semester were to identify the resonance frequencies for unstable types of xenon. So the resonance frequencies for all stable types of xenon, which is the frequency that your laser needs to be at in order for xenon atoms to be trapped. Those have all been identified for stable isotopes, but there are a couple of unstable isotopes that are really important because those are the ones that will show up at a nuclear detonation that haven't been identified yet. So we were working on identifying particularly xenon 131M, which we chose because of its really long half-life, so we'd have plenty of time to work with the sample before we lost it. Unfortunately, we hit a couple of roadblocks in our progress and we were unable to actually identify the resonance frequency for 131M because we did not feel comfortable ordering a sample because our equipment wasn't, the signal to noise ratio that our equipment was functioning at wasn't satisfactory to the level of performance that we would like in order to order the sample and be working with radioactive things in the lab. And also the sample is quite expensive. So this is a picture of the background noise that we see in the magneto-optical trap. And as you can see, there's a lot of scattered light because we do have lasers coming into a reflective surface. And so we have a lot of scattered light. This is a picture of a xenon 126 MOT, which is what we call it when we have a blob of xenon atoms that are trapped in the center. And as you can see, there are some differences. Oh, sorry, I have to go back. As you can see, there are some differences. There's a very definitive change, but the problem is that xenon 126 is a stable isotope, and this is about the level that we would expect that our xenon 131 would be. This has a very similar number of atoms, a relative concentration in air. So this is about the number of xenon 131M atoms that we're expecting in our sample, and this is not quite satisfactory enough. We did some image processing and we have gotten it to look about like this, which I know there's not a significant difference to the naked eye there, but we have the signal to noise ratio about to a 0.6. We're hoping to increase the signal to noise ratio over the next couple of semesters that cadets are working on this project to by a factor of 10. And we have a couple of things that we're trying, including image manipulation and physically changing the structure of the system in order to increase the signal to noise ratio. And then once we get our once we get the signal to noise ratio high enough that we feel comfortable ordering that sample, getting the resonance frequencies from the radioisotopes of xenon should be relatively quick. This is a summary of all of our references. Are there any questions?
If folks have questions, you're welcome to raise your hand, put them in the chat. So Piper, I have a question for you. What was it about this project that excited you the most to do these experimentations?
So I am, I just recently commissioned into the Air Force. And so starting in August, I'll be working at the Air Force Technical Application Center doing nuclear treaty monitoring. And so that was one of the things that attracted me most to this project, was the ability to do something that would be directly correlated to the work that I would be doing later. And I also think that it is really exciting to be working on something like this project, where once we get our data, once we build a system that does work and DITRA and INSARC have a lot of confidence in, we could be seeing these this equipment, this theory, these processes being used on actual Air Force planes within the next 5 years. And that's always really exciting as a physicist, to get to work on something that could so quickly become something that people are actually using, because normally as a physicist, you're working on theory, and engineers kind of have the privilege of being able to work on something that's very physical and produces something that's actually going to benefit society. And so that was something that I definitely really liked.
Awesome. Thank you. If there are other questions for Piper, please ask. And I'll wait one more minute, and then we'll enter our everybody turning on their video in a minute, and we can ask some questions as a group. Okay, so we have about well, our session goes until about 12:15, so we're running ahead of schedule, which is really great. So let's have some time for some group Q&A. So if all presenters could please turn on your cameras, and you're welcome to unmute yourself as well. Okay. So I have a question for all of you. And it's not it's not specifically about each of your projects, but so I'm a librarian. And so I want to hear about like your struggles of your research process, and like finding like literature, and like, I want to hear that story about your process. And so I was wondering if you could just share some of like about your research process, finding information to inform your inquiries or to shape them. So anyone want to go first?
I can go first. So a lot of the resources that I had were actually provided to me by the lab that I was working with. And so that's where I got a lot of the prior work. I also was working with like an unpublished manuscripts that had been done, or had been, completed in the lab before my time. And so a lot of what I was doing was going through the resources provided in that manuscript, and then like essentially taking the sources from that and going through them, combing through them, because a lot of the prior work in the subject, as I mentioned, was done a very, very long time ago. And so a lot of those sources are outdated. So it was going through like resources provided to me through the lab.
Great, thank you.
For me, I kind of had to rely on several different sources just because of the nature of my project. So a lot of the initial stuff came from, before I even started the project formally, I was volunteering at the organization that I worked with. And so a lot of it came from people who had already done some research into it, who were working for the organization, that sort of pointed me in the right direction. And then sort of like what Megan just said, a lot of the research was just like finding something that I liked and then combing through the references, trying to like dig as deep as I could. And then, yeah, also relying on, especially for like designing my project, since I had to sort of like come up with exactly how I wanted to carry out everything about this project. It was also really helpful to, I took a class that was specifically on qualitative or on mixed methods research. And so there was a lot of reading that came from that too. So that was really helpful as well.
Great, thank you.
I can go next. I would say, you know, I think it's cool that Blake kind of really formed his own question. I was lucky that I worked on a lot of prior research, and so kind of the direction I was going in, and kind of the questions that I was working on, I already had. So that part was super challenging. But I would say one of the big challenges that I faced, I worked a lot with computer coding, and basically, there are so many bugs that you can run into. I remember I spent several weeks. So I built a simulation, right? And we would run millions of trials. And for a while, we could only get like 100. It took like several hours to do like 100. And the idea was to run millions. And so we had to like scan every line in the code to see what was causing it to be so slow. And it took a really long time to figure out why it wasn't working as well as we thought it was. And then we realized it was one line of code, and we changed that one line, and suddenly we could do several million in the same amount of time it took us to do like 100. And so I think so the big thing I took away from that was like figuring out where the slowdown was, because if we had stopped it like 3 weeks earlier and said, hey, why is this so slow? We need to figure this out, and kind of went through that, we could have saved several weeks of research. So that was a pretty big learning experience for me.
At the beginning of my project, I think just because of the structure of the physics department at USAFA, my experience was very similar to Sam's, because you're coming in on a project where they've already done a significant amount of work. They're very used to working with cadets, so they know exactly what to have you do. And so at the beginning of the project, my main role was to help automate the data taking process. And that was just a lot of coding, which I'm very familiar with, very comfortable with. And there's anybody who works on MATLAB knows that there's tons and tons and tons and tons of documentation that's very readily available. And then about midway through the semester, about when we hit mid-March, we realized our signal noise ratio is really bad. It is not going to be worth, to put it into context, the sample of radioactive xenon that we're hoping to test costs about $15,000 per sample, which is like, in laboratory money is like not that much, but it's not an insignificant amount of money. And you don't want to be ordering $15,000 samples, and then you don't have anything to show for it. And then the like lab directors like, what are you doing? And so from then on, we were basically trying anything and everything to increase the signal to noise ratio. And that was when we started having to do a lot of research, read a lot of very obscure papers, and very quickly we got into really advanced image manipulation processes, very advanced, reading tons of papers about dark noise and reading all about like how cameras work and trying to understand exactly what was happening. And that was when we hit like a lot of paywalls, and it becomes a lot more difficult to understand with an undergraduate degree exactly what people are talking about. And it gets very advanced very quickly, and it was pretty difficult to keep up.
Great, thank you. And if anyone has if anyone else has questions, please raise your hand. Even if our panelists have questions for each other, please feel free and ask. Okay, I'll ask another one. Where do you see your research going next? And what impact do you want it to have?
I can start this one. So for my project, I was mostly focused on like identifying things, but I didn't really get the chance to like look for solutions. So a lot of mine was oriented around trying to identify where the project or where the issues were stemming from. But I think if given the opportunity, I would look more into like, one, trying to make it more representative than just Lane County, so just one county, and two, trying to figure out how to like target approaches to reduce vaccine hesitancy, or at least to provide more information to people. So yeah, I think that would be like forefront of my mind for future directions.
I think that for me, the next step would be to look beyond the simple, look at every single IP address that was active and look into classifications of addresses. So has this address been classified as malicious or is it benign? Because I think that it's this very, very important distinction to make, especially because we hope that the research will contribute to like network monitoring solutions. I think that making the distinction between all addresses and simple like malicious addresses would be very integral in supporting that direction.
So I would say that our research was based off of prior research for a different element for cesium, and so but as we worked throughout the entire semester, one of our goals was to there were a lot of things that were hard coded for cesium, and we were trying to change it so that it could be easily adapted not only from cesium to potassium, but from potassium to other elements. And so I would say, and obviously, well, so first off, we didn't get the results we wanted. So the project is still ongoing in that we're trying to get a simulation that perfectly, or not perfectly, but pretty closely represents what radiation trapping would look like in potassium. But for the future, it would be basically making it so it would be really easy to transition to take this code and transition it from potassium to another element, so that we don't have to, someone doesn't have to go through this entire process a million times for each element and see what that looks like.
Similar to Sam, my project is definitely still ongoing, and hopefully we get our signal to noise ratio up, and then we can order that sample, and then start categorizing radioisotopes of xenon, which is really exciting because nobody has ever done that before. And so hopefully that will get us some pretty unique results that we can publish and then can turn into something that has practical use for the Air Force.
Great, thank you. So the next question I have has to do with data management and reproducibility, because that's my wheelhouse, but I work in the humanities. So I'm curious to hear about what were all of your data management processes like, because your areas of focus are so different. And I'm like, I want to hear about science reproducibility. I want to hear about like interview reproducibility. How do you do it?
I can start just because I have a lot of frustration that working with lasers is very, very difficult, and they're very touchy, which is very frustrating because, you have a rainy day up in Colorado Springs, which happens a lot, and the pressure in the area is completely different, and your laser does not work. And it can be 50 megahertz to the left or to the right of where it was the day before. And so trying to account for all of that in your data taking can be really, really difficult if you're not in an isolated laboratory, which we don't have the privilege of being. And so what we had to start doing was we had to start, in addition to categorizing the laser frequency, we also had to start looking at the surrounding temperatures, weathers, and dig into how that was going to affect the laser, and start to try to build a program that can anticipate, or can basically take the temperature, weather, pressure information and use that information to translate the recorded laser frequency to the actual laser frequency, which is a problem that I wasn't really anticipating, but was definitely a very interesting thing to try to solve.
I feel like I was very fortunate for a couple different reasons as far as data management goes. First, because like I said, so the quantitative aspect of my project was through a larger project. So they already had a full data management plan. And this is like a project that they've been working on for like almost 2 years now. So they sort of had it down to a science. So I was really in charge of the data management for the interview component that I spearheaded. And I mean, honestly, I'm sure that it would get more difficult as you scaled up. But just considering the fact that, so I basically had 41 interviews that I had to keep track of for like, so I had the actual audio and then I had the transcriptions, but I used a qualitative analysis software called NVivo that is pretty good at managing all of that stuff. Like it's sort of integrated within the app. So yeah, I mean, I didn't have millions of data points to keep track of. So I don't know. That's my answer, I guess.
I guess I was dealing with a rather large quantity of data that is stored by the computer science department at the university. So there was a lot of like uploading and offloading the data to remote servers so that I could process it on those remote servers and run things overnight. Luckily, the file format that of the data that I was using is fairly common in networks research. And there are a number of like libraries for processing it that are quite common. And so when I like created my sets of IP addresses, I was building off of the skeleton that one of those libraries had provided. And then those sets were then kept in output files, which again, stored on the remote server. There was a lot of file management. And I think that was probably one of the most tedious things to navigate. But overall, it was mostly just a matter of keeping things saved on the cloud in repositories and making sure that, you know, I wasn't clogging up the remote servers with too much information.
I would say that I definitely learned a lot of lessons about how not to manage your data wisely. And it was kind of interesting because especially early on in the semester, we got a lot of results that were very wrong. And like, I mean, it was you were testing things out, right? And so you'd run the simulation and it would pop out something that was completely wrong and you knew it was completely wrong. And so you kind of get in the habit of just throwing it out because you know you're looking for something else. And so like kind of as we started progressing, sometimes it would get closer and closer to looking like it was right. And then it was a matter of how many files do we have hundreds of files that are mostly wrong, but maybe a little closer, right? And so, but I'd say so that was a struggle was figuring out what to keep and what not to keep, because you're kind of looking through files and it takes a while to load sometimes, especially right when we had those bugs in and you didn't want to save a bunch of files that just didn't work very well. But the biggest problem I learned was just kind of communication with my partner, because he was working the experimental side of things and I was working the computer simulation side for the most part. And so we actually realized we were supposed to present for our mentors at one point. We realized that we hadn't been taking the same data. He was taking different temperatures and pressures than I was. And so our results were completely different because they weren't even the same. We weren't even, we couldn't even compare them at all. And so at the last minute, I had to rerun the simulation a lot to try to like match the numbers. And so, I mean, that was a very, very easily avoidable problem, right? If we had just talked, you know, the day before or whatnot, we would have realized that, you know, or a couple of weeks before, we would have realized we wouldn't have had that problem. But I mean, sometimes things just happen. He'd go down to the lab, he'd try to run a certain temperature, and then he'd realize that the way the experiment was set up, he had to do a different temperature, a different pressure, or it made more sense to do that. And I'm running, you know, on a computer, a lot of pretty like numbers look really nice, like 100, 200, 300, whereas in the lab, it's like 150 or 160 works better. And so, yeah, just communication was a big thing I learned about that.
Yeah, that's always, I do a lot of interdisciplinary collaboration on research teams, and that is always one of our biggest challenges is who's on first, who's touching what data, where is it stored, when's it left, what's the latest version of it. And it's so different depending on what disciplines you're coming from. So great. Well, thank you all so much for sharing. We are at 12:08. And so if anyone has any other questions, let's ask them now before we say goodbye. Okay. We have waited. Well, thank you all so much for great presentations, and kudos to you. Doing presentations on Zoom is really challenging. So good job. You all four did fabulous.
I agree. Good job, guys.
Good job. Okay, we are going to stop the recording now. We're done. I think we're done.